Hello hiers and welcome to Enthalpy of Combustion. This is our lesson 6. So we start here. So question 1, write the definition of enthalpy of combustion. And then question 2, when 1.7 grams of sulphur was completely burned in air, the heat produced warmed 110 grams of water from 18 degrees Celsius to 38 degrees Celsius. Calculate the enthalpy of combustion of sulphur. So pause this video, do the starter, and then I'm just going to go over the answers. So question 1, write the definition of enthalpy of combustion. Here it's here. So it's the amount of energy released when 1 mole of a substance is burned in excess oxygen. Yeah, straightforward, boom, done. Question 2 we're going to do together. So it is an enthalpy of combustion one, so we split our page into 2. Okay, and our 2 headings, EH equals CM delta T, and EOC, which stands for enthalpy of combustion. And remember, 1 mole equals the GFM. Yeah, that's what we mean by a mole, that's the GFM. Right, so let's put our wee sidebar. So EH CM delta T. So EH we don't know, C is 4.18. M from the question, remember we don't use the mass of sulphur, we use the mass of water, which is 110 grams. We divide that by 1000 to get it into kilograms, so it's 0.11 kilograms. Okay, and the waters went from 18 to 38, so that is a 20 degrees Celsius change. So we add all those values in, so 4.18 times 0.11 times 20, and if we check on the calculator, so 4.18 times 0.11 times 20, I've got 9.196 kilojoules. Yeah, so there's 1 mark. Enthalpy of combustion, so it is sulphur, which is just S. And if we check in the data booklet, the GFM of sulphur is 32.1 grams. And remember, that is our 1 mole. Okay, so 1.7 grams gives us, remember EH is the only thing that can cross over, so 1.7 grams gives us 9.196 kilojoules of energy. However, we don't want that. We want how much 1 mole gives us, which is 32.1 grams, and that gives us X. Okay, and we do a simple cross multiplication. So X equals, the 2 numbers that are connected with the cross are multiplied, so 32.1 times 9.196, and the number that's connected to the X we divide by, so 1.7, and that gives us, if I just do that, so 9.196 times 32.1 hit equals, divide by 1.7, and what we should get is 173.64 kilojoules per mole. Yeah, and remember, because it's enthalpy of combustion, you need to have that negative sign. What does the negative sign tell us? It's exothermic. Energy is getting released. We're losing energy. Okay? So that's it. You can check that. Right. So this is our title for today, Enthalpy of Combustion, continued. I'm just going to make a wee couple of notes before we go. So, in exothermic reactions, okay, because energy is getting released, it's negative, and then that raises the temperature. Okay, because the energy from the substance gets released, and that energy that got released heats the surrounding area, so the temperature increases. If it's an endothermic, it's literally just the opposite, so it means it's got a positive sign, and because energy is getting taken in, that means the temperature decreases. Okay, so that's just a wee note there. Right, now, in experiment, okay, so the experiment that we would have done in class, but the one you did at Nat 5, okay, where you got the spirit burner and the heat shield. So in experiment, to calculate, and this is quite important because this comes up as past paper questions all the time. In experiment, to calculate the mass of alcohol, we need the mass of the burner. Okay, so the mass of the alcohol, so we need the mass of the burner containing the alcohol at the start and end of experiment. Okay, so that's your before, the mass of the burner before and after the experiment. Okay, so we take the mass of the burner before it, okay, we'll then heat it. In the experiment we normally heat it for 3 minutes, and then we wait again, and then we calculate the difference between the two, and then whatever the difference is, that's how much alcohol has been used. Okay, so we need the mass of the burner at the start and end of the experiment. So that's your before and after mass. Okay, and that tends to come up quite a lot. How do we calculate mass of alcohol or mass of propane, whatever? You need the mass of the burner before and after the experiment. Okay, right. What we're going to do now is something that we all loved from National 5, is balancing equations. Yeah, I'm excited as well, don't worry. Right, so I'm going to shorten this. So for enthalpy of combustion equations, balance in this order. Okay, so first one we want to balance, you want to balance carbon. Okay, second one you want to balance is you want to balance hydrogen, and then the last one you always want to leave to the end is oxygen. Okay, so for example, let's do methane. Now remember a definition of enthalpy of combustion. It's the energy released when 1 mole of a substance is burned in excess oxygen. Now if we've got excess oxygen, we've got a plentiful supply of oxygen, that means it's undergoing complete combustion. Okay, and then from National 5 you need to know that from complete combustion the two products that we get are carbon dioxide and water. So if we go for methane, that's CH4, we're burning it in oxygen, okay, and then because it's complete combustion we're getting carbon dioxide plus water. Now you don't really need to know this for enthalpy of combustion, but if it was incomplete combustion, can you remember what we get? The water stays the same, but we get carbon monoxide instead. Okay, but just know that for enthalpy of combustion you're always getting carbon dioxide and you get water as well. So that's our enthalpy of combustion equation. So we need to balance it. So balance the carbons first. So how many on the left? 1. How many on the right? 1. Then balance the hydrogens. How many on the left? 4. How many on the right? 2. Okay, so 4, 2. We put 2 there. Yeah? Now, the oxygens are always the hard part, and then my advice would be to draw the number of oxygens below. So we've got 2 on this side, yeah, we've got 2 here, and remember we've not got 1 because that's multiplied by 2, we've got 2 here. So in total we've got 4, and then we've got 2 on the right side, so balance the oxygens by putting a 2 there. Yeah, straightforward. Now if we do ethane, so ethane, you need to know C2H6. Again, we're burning an oxygen and we're getting carbon dioxide plus water. That never changes, and then all we need to do is balance it. Okay, so balance the carbons first. How many on the left? 2. How many on the right? 1. So we put a 2 there. How many hydrogens? 6 on the left, 2 on the right, so we put a 3 there. Okay, then I would write how many oxygens you have below. So we've got 2 on the left, we've got 1, 2, but it's multiplied by 2, so we've got 4, yeah, and we've got 3 here. So in total we have 7. Okay, now we've got 2 here, we've got 7 here. Now remember, because it's 1 mole of a substance, this number can never change. Okay, that always has to be 1, because it's 1 mole of a substance is burning. So what number times 2 gives us 7? And you need to know that is 3.5. Okay, so 3.5 times 2 gives us 7. You can either write it as 3.5 or you can write it as 3.5. It doesn't matter. Okay, so we're bringing half numbers into it now. You can only ever get a full number or a half number. You can't get a quarter, you can't get an 8 for 3/4, whatever. So you can only get half numbers. My advice would be multiply it by 3, that gives us 6. Okay, multiply it by 4, that gives us 8. So if it's not 3, it's not 4. 3 is too little, 4 is too much. It has to be in the middle, so 3.5. Okay, right, let's go for ethanol. Okay, because we can burn alcohols as well. So ethanol, C2H5OH. Adding burning water, oxygen in that, so that's carbon dioxide plus H2O. So again, balance the carbons first. So 2 carbons, 1 carbon, we put a 2 there. Now remember, we've got 5, 6 hydrogens here. Don't forget the H from the OH. So 6 here, 2 there. So we put a 3. Now, as always, I would put the number of oxygens, put the number below it. So we've got 2 oxygens there. We've got 1 oxygen on the alcohol. People tend to forget that. So that's 3. We've got 1, 2, multiply it by 2. We've got 4 oxygens there. And we've got 3 oxygens here. So that is 7. So again, we've got 3 on this side, 7 on that side. How do we do it? What number times 3 gives us 7? If we times it by 2, it gives us 6. If we times it by 3, wait, what? Yep, if we times it by 2, we get 6. If we times it by 3, we get 9. So oh, sorry. Right, we've got 1 here. Okay, 1 here's already. Now, what number could we times that by to give us 7? Okay, if we times that by, if we put a 2 there, that would give us 4 plus 1, that would give us 5. That's not enough. Now, if we put a 3 here, okay, we times that by 2, that gives us 6. Add that to the 1 that we've got there, that gives us 7. Okay, so the alcohols are a wee bit more difficult. Now, I'm going to do one more. We'll go for propane 2-ol. Now, that is C3H7OH plus oxygen gives us carbon dioxide plus water. Okay, so balance the carbons first, 3 on the left, 1 on the right, so we put a 3 there. We've got 7, 8 on the left, 2 on the right, so we put a 4 there. And do the oxygen, so we've got 2 here, 1 here. Okay, we have 6, 2 times 3, 6, 4 times 1, 4, so we've got 10 on this side. Okay, now that one there can't change, it's only this one we can change, so that means we need this oxygen to be 9, because 9 add 1 would give us 10. So what number times 2 would give us 9? If we times that by 4, it gives us 8, that's too little. If we times it by 5, that gives us 10, that's too much. So it has to be in the middle. So it would be 4.5, because 4.5 times 2 gives us 9, and then add 1, that gives us 10. Okay? Right. Now what we're going to do, we're going to do some questions, variations on the type of questions we were doing on Friday. Okay, so I've already written out the questions. You guys can pause the video, you can do that as well. We're going to go through them, and then that will be us. I'll put up some work, and then yeah, that'll be it. Right, so pause the video, get the question done, let's go over it. Right, the enthalpy of combustion of ethanol is given in the data booklet as -1367 kilojoules per mole. Using this, calculate the mass of ethanol in grams required to raise the temperature of 500 grams of water from 18 degrees Celsius to 100 degrees Celsius. So usually the question asks us to calculate the enthalpy of combustion, but it's given us the enthalpy of combustion. We need to calculate the mass this time. So instead of calculating enthalpy of combustion, we're calculating the mass. So we do the exact same thing as we normally would. We'll split our page into 2, and we put our 2 headings. So EH equals CM delta T and enthalpy of combustion, and remember 1 mole equals the GFM. Yeah, we do have information that can calculate EH, so let's do that now. EH CM delta T. So EH we're trying to find out. C, because it's water, always 4.18. The mass of water is 500 grams, so divide that by 1000, we get 0.5 kilograms. And the waters went from 18 degrees Celsius to 100 degrees Celsius, so that's a change of 82 degrees Celsius. So add that in, 4.18 times 0.5 times 82, and just do this calculation with me, make sure I'm not making any silly mistakes. So I'm getting 171.38 kilojoules, and there's your first mark. So far we've not actually done anything different. Yeah, our next bit, ethanol, so it's C2H5OH. Let's work out the GFM. So start with hydrogen, we've got 6 of them. Then oxygen, we've got 1, so that's 16. And then carbons, we've got 2, so 2 times 12, that is 24. So that is 46 grams. And remember, that equals 1 mole. So 46 grams is 1 mole. Yeah? And again, so far, nothing's changed. Yeah, we've got 2 marks for doing the exact same thing as we always do. Now, the next part, this is the important part. Okay? Now, usually, we would take this number, well, we still will, take this number across, and then the amount of alcohol that's burned would give us that amount of energy. However, we're trying to calculate the mass of ethanol in this case, so we don't know what the mass is, so we show that by putting an X. So X gives us that amount of energy. Okay? Now, the next part is 46 grams. Gives us how much? Well, from the question, 46 grams is 1 mole, so the enthalpy of combustion, it tells us the enthalpy of combustion in the data book is given as negative 1367. We don't need to put the negative in, so 1367, and that's what's changed. Okay, so instead of the X being here, the X is now on the mass side. Okay, and this can be quite confusing. A lot of people get it mixed up, but the more practice you get, the easier it becomes. So X gives us that, 46 grams gives us 1367. Now, as we've always been doing, cross multiply, and to get X, multiply the 2 numbers that are connected together, so 46 times 171.38, so 46 times 171.38, and then divide that by the one that's connected to X, which is 1367, and if we do that, if we can do that together please, 46 times 171.38 divided by 1367, I'm getting 5.7, and if we round up, 7 grams. Remember, it's grams. Whatever side the X is on, the units have to be the same. So 46 grams, that's 5.77 grams, and that's what the question's asked for in grams. So that's your answer there. Yeah? That's your third mark. Right, let's do question 2. Calculate the mass of methane that would produce 21.3 kilojoules. You may wish to use the data booklet. Now, I always love that statement. You may wish to use the data booklet. What's the SQA telling you? If you get a question that says you may wish to use the data booklet, you better use the data booklet. That's what they're saying. So EH equals Cm delta T, enthalpy of combustion, remember 1 mole equals the GFM. Right, we don't have the mass of water, we don't have the change in temperature. What we do have is the EH. Okay, so we don't even need to do the calculation. So the EH equals 21.3 kilojoules of energy. That's it. Yeah. Now, calculate the mass of methane that would produce 21.3. So we've got methane. You should know that methane is CH4. So that's 4, 12. So that is 16 grams, and that is 1 mole. Yeah? Bring that across. So calculate the mass of methane that would produce 21.3 kilojoules. So we don't know how much produces 21.3. So we put X gives us 21.3 kilojoules. Now it said you may wish to use the data booklet. That is page 10 of the data booklet that's asking you for. Now I've got page 10 here, yeah, and you'll notice it's got a table at the top here, and one of the heading is standard enthalpy of combustion. That's what we're after. Okay, now we're after methane, so if we start methane there, we go along. So the enthalpy of combustion of methane is minus 891. Okay, so you don't need the minus, you can just put 891, yeah? And how much is that? So if that's the energy release when 1 mole is burned, how much is 1 mole? Well, we've calculated it, 16. So 16 grams would release 891, okay, kilojoules. And all we need to do now is cross multiply, so x equals 16 times 21.3 divided by number connected to x, 891, and what are we getting? Do it with me please. So 16 times 21.3 divided by 891, I am getting 0.38 grams because the x is on that side, yeah, 0.38 grams, and that's it, yeah. You'd only get 2 marks for this question, you would get 1 mark for that and then 1 mark for that. Yeah, you didn't do any calculation here because the question gave you it, so it would just be 2 marks for that, and that's it, yeah. I've got one more prepared for you. So calculate the mass of methanol that would produce the energy required to raise the temperature of 500 centimetre cubed of water from 17.2 degrees Celsius to 51.7 degrees Celsius. There's that phrase again, you may wish to use the data booklet. So what does that mean we're going to do? We're going to use the data booklet. So again, nothing changes. Enthalpy of combustion calculations are all the same. You split your page into 2 and you get your 2 headings. EH equals CM delta T, enthalpy of combustion, and remember always to write 1 mole equals the GFM. Right, now we do have the mass of water, we do have a temperature change, so we can use this calculation now. So EH equals question mark, C equals 4.18, the mass is 500 centimetre cubed, so that's 0.5 kilograms, and the temperature change, 17.2 going to 51.7, what's that, that's 34.5, just double check that for me, hires, 34.5, and just put that in, so 4.18 times 0.5 times 34.5. Okay, let's do this calculation together. So 4.18 times 0.5 times 34.5, I am getting 72.105 kilojoules. There's 1 mark, boom, done. It's methanol, so let's calculate the GFM. Right guys, that's my door. I'll be back 2 secs. Hey. Sorry, hires, that's me back. Right, so 4 hydrogens, 4, 1 oxygen, 16, and we've got a carbon here as well, which is 12. So if we add all that in, 32 grams, that's our 1 mole, like that. Yeah? Right, now, we bring that number across. We don't know the mass, okay, because we have to calculate the mass of methanol that would produce this energy. So X gives us 72.105 kilojoules, and 32 grams, again, we don't know what it would give us, but it does say you may wish to use the data book. So let's use the data booklet, page 10. Now we're after methanol this time, so there's your enthalpy of combustion. Methanol, go along, that's minus 726. Yeah, so again we don't need the minus in this case, so 726 kilojoules, 32 grams would give us. do what we're used to, cross multiply. So x equals 32 times 72.105, divide that by 726, and x equals, okay, so let's do this, times it by 32, divided by 726, x equals, I'm getting 3.1, round up, 8 grams, and that's it. Okay, 1 mark for that, another mark for that. Boom, done, easy. And that's it. Okay, right, I'll give you a few questions to do. It won't be a lot, it'll be a few questions, and then just send it in via the Teams assignment. Right, thank you. Oh, wait there, sorry. Before I go, just make this wee note here. So enthalpy of combustion values are found on page 10 of the data book. Okay, and it's not every enthalpy of combustion value, it's just a few of them, your methane, ethane, propane, etc. So yeah, that's me now, thank you.